Uh, Good evening, everyone. Welcome to the fourth week session, like for the course of a statistic for biomedical engineering. Is my voice is audible? Can you confirm? Hello, hello. Can you confirm that my voice is audible? Hopefully, the that voice will be audible. So, welcome to the fourth week session on the course of a statistic for biomedical engineering. I am that MD Azad Raza. PMRF scholar in the Department of Mechanical Engineering in Tiruchirappalli. So in the first 3 week, we have seen the course, like we have seen the session on the biostatistic, what is the applications and all. And then we have seen second week, like what is the role of the that probability and why, like what are the types of the probability that we have. Then we have discussed some sort of description of that statistic. Also, we have seen that what is the mean, that mode, and then the median we have seen. Then we have seen the theory that is related. Then we have seen the probability distributions we have seen. Then we have seen the expectation, how it different from the mean, and then population variations and all way. So fourth week we'll see that a very important part, that is central limit theorem. Okay, so this week we will see like what is the central limit theorem, then confidence interval. It's all the we are going to make the foundation for that hypothesis set testing and all, and we will introduce some basic of that hypothesis testing also. So till last class we have seen that is the probability distribution we have seen. Like we have seen the Poisson distributions, then we have seen the binomial distributions,
Sir,
and
excuse
we
me.
have discussed
You are on mute, sir.
sorry. Okay, sorry. Is it audible now?
Yes, yes, yes. Now it is.
Oh, yeah. Okay, thank you. So, this week, like in the first 3 week, we have seen the what is the statistic course and all, like what is the application of biostatistic and all. Then we have seen the what is the need of the that statistic, then role of the probability, and we have seen. After that, we have discussed the some description of the statistic like mean, mode, and that is the median. After that, we have seen that what is the probability theory. In that, we have seen the distributions also like binomial and the Poisson that distribution we have seen. Binomial, like we are going to apply the when the possibility or outcome chances is higher and the sample size is low, so that will apply the binomial distribution. But when we don't when we have the possibility or outcomes will be very less, and then but the that the number of samples is very high, so we are going to apply the Poisson distribution. So these two distributions is actually a discrete distributions. After that, we have seen the normal distributions. That normal distribution is a continuous distribution. Before that, we have seen the that the uniform distributions also we have seen. So actually, the uniform distribution is an ideal case. Like we are going to assume like it's going to be like always the uniform uniformity will be there either in the occurrence or either in the event or either in the sampling, and all that will be the all the uniform will be there. But in the ideal case, that is the case. But if we come to the real life example or that in the application part, so that might be not always true. Okay, so till last class we have seen like the distributions. We have solved the problem based upon the binomial the distributions and Poisson distributions, and we have introduced like basic of what we can say and the normal distributions. So today we'll start with the normal distributions, and then we'll solve one or two problem, and then sometime I will show you how to But we can say see the tables also. A statistic table is also very important because sometime it will be given or sometime it will not be given. So you should know that like what is the how we have to see the tables and all. So we'll solve the problem. Then after we'll going to jump into the sampling. We'll see, and then how can we define the number of samples and all that we can say. So fourth, and then we'll introduce the what is the hypothesis testing. Like why do we need the hypothesis testing? Like this is to make the grounds and all. So we'll start from the last session only. Like we have seen the what was the normal distribution. That normal distribution actually is approximately that will going to occur in the that every that is the situations. It's going to perfectly symmetrical around its mean. And if you're going to see the sum, what is the properties and all, so we can see it's going to be like symmetrical about in the mean. So it's going to mirror image on the either side. I think this we have seen that. Just I'm going to brush up like how it's going to equal. For this, the case of normal distributions will be the mean, the median, and then the mode will be going to be equal. It's like it's going to be like this one. So in that case, all will be same. And the total area under the curve is nothing. It's going to represent the total probability. It's going to be always one. So there is nothing much of to discuss. So this is that is the 50% positive side, like one side, then second side will be this one. So it's going to 50-50, it divided. And this one is going to mu. So mu it's going to function mu and that's sigma. Because we have seen the here normal density function is going to f of x 1 upon 2 pi sigma e to the power minus x whole square. Like upon 2 whole square. Then the further we have a like the normal distribution, like a standard normal distribution. What is the difference between the normal distributions and that standard normal distribution? In that case, we'll be having the mean of 0 and a standard deviation of 1. So means when we are going to plot the curve, it's going to like this. So it's this value will be the 0, mu is equal to z is equal to 0. Okay, so it means that mean is equal to 0 and the standard deviation will be the 1. So and the z value will be x minus mu by sigma. So the formula will become like this, and that is going to the limit of minus infinity to plus infinity. Okay, so actually it's earlier it was the variable of the two, like we should know the value of the mu and then sigma. But now we are converted into the sigma, like we have to integrate in terms of mu and sigma. But now it's a simplified version of that normal distributions. It's a standard normal distributions. So based upon that, we can see some problems also. Standard normal, if you're going to see, so it's going to be like if you're going to have this one sigma at the mu is equal to 0, sigma is equal to 1. But if you're going to like that the single sigma, and then so in that case, it's good. They're going to take the 68% of the area it will cover. It means like the chances of the error will be the 1 minus 0.68, it will be going to 32%. But if you're going to increase the sigma, it's a 2 sigma, it's become a 95%. This reason will say that what is the confidence interval, or the either side will be the it's going to rejection result. So when the sigma, like sigma is going to increase, so that our that error is going to be like decrease. Like error means the probability of not completion and all, it's going to decrease. Like how come? Because the z is equal to x minus mu by sigma. Sigma is going to increase, so z is going to be decrease. So it's an inversely proportional and all, but probability is going to increase. Like, but the probability is going to increase. So that we'll see from the tables also. When we are going to take the point 0 to 1, like this is a 0.313, and then either case we can just like what we can say minus 1 to 1, it's going to be a summation of the both. If you're going to take the one side 0, 1, minus 1. So probability of 0 to z of 1, it's become 0.313. That we can see in the table. Okay, I will show you the table also. Just 1 minute. Okay, so this is the table actually. It's a two-tailed table actually. If you're going to see for the one, and this is going to give the value of what we can say, like just 1 minute. So here we can see like when for the corresponding z point one, and then what is the after point, what will the values that from here we can see actually. So once we solve the problem, so that I will show you like how it came and how it will come. Okay. So if you come about, let's say, when we're going to take the that when the value of the z is equal to 0.745, so that the area will be the 50%. And if that z is equal to 1, it's going to be 68.26%. It's like that the minus 1 to plus 1. When you're going to increase the z, it's going to that the 95.44%. If you're going to increase the z like 3 sigma and all, so it becomes 99.73. So similarly, it's the on the similar basis, we have the concept of that the six sigma company and then 4 sigma company and all. Nowadays we are dealing about the 6 sigma and all, so it means 99.999 something it comes into the picture. So means that there is still chances of that error will be there. Let's say I told that the last class one example, like let's say that the thesis is there. They are saying they are the following the Six Sigma, that the rules and all. So means they will say I am going to deliver the any ongoing project or the project I have taken. There is a chance that 99.999%, but still somewhere there is a pinch of salt. It's going to be like 0.001%, that sometimes they're not going to deliver. Means it's a margin of error is very less in the case of when the sigma is going to increase. Okay, so here also that the similar thing means when you're going to increase this, so that the area under the curve is also going to increase. It means that our accuracy and all chances or the probability is going to get increased. So can we solve the problem based upon that? Like they are saying, what is the probability of the obtaining a z value at least? Can anyone tell like how can we solve at least of 0.18 z? It will like this, means at least means equal or greater than of whatever the value they have given. So we'll draw the this curve. Z is equal to 0. Let's say this is going to be 1 and this is going to 1.58, this one and 2. So they're asking what that is the probability of this side they're asking. So what will be that will be the probability? Can anyone tell? That is the already z value is given. Can we do like this? 1 minus of p of z of less than 1.58? Because eventually that if we're going to give this value, can we give it or not?
Yes, sir.
So if you see the like z value of 1.58, what is the value? It will come. Anyone have the table? Hmm? Or I'll show. Z value of 1.58. 1.5 of 8. 1.5,
0.94. 94.
0.9306. Is it? No, it's a 0.9429. Is it?
Yes, sir. Yes.
Yeah. So 1 minus 0.94, like 1 or 2 it came. So that will be the probability. If you're going to 0.0008 or 6 it will come. So 6% will come into the picture. So that is the probability of obtaining the value Z value for that is the some cases was there. So now we have the second question we have. So they have given the with the mean. First you try, I will solve the next. Huh? First one is they have given the mean given value mu is equal to 100 and a standard deviation they have given is equal to 15. Now they are saying that a person with an IQ of greater than 150 has IQ. What is the proportion of the population has a high IQ? It's again simple question. So that they are asking x is equal to greater than 115. So what is the first step? Can you tell? Z is equal to x minus mu by sigma. 115 minus 100 by 15. So 15 by 15, 1. What is the one case it will come? This
Uh,
means
0.84.
0.84, but they are asking that greater than 1. That may going to that's going to one side only, na? So we have to decrease. Can we do like this?
Yes, sir.
So it's going to be like how much? 0.34 something will come. Is it? Something will come. So it's going to 0.016. No, 0.15787. So 15.87. Or either there is one more way you can do. P of how much? Z is equal to less than of 1. 1 minus 0.8417. You can do 0.1587. So that the both cases are same. Both will be the same. Is it clear? Either you can go like this or either you can go directly like this. 1 minus 0.8417. So that you will get the same answer. Is it?
Yes, sir.
So now one more question we have. Like I'm just giving the brief like how come it's going to use like it's going to useful when we're going to see the another table like t-test table and all. So now the question we have here. The mean that the yield for a 1 acre plot is 662 kilos. Means they have given the value of mu 662. Then after that standard deviation of is given 32. Assuming that normal distribution, how many acre plot in a batch of 1000 plots would you expect to the have yield of over 700 kilo? Means first case they have given x should be greater than of 700. Second case we have a x of less than of 650. Third case we have a what is the lowest yield of the best like 100 plots. So we have to calculate ton by 1000 like 10% they are saying. No, like so it will give will get the 10%. Is it? So means it's going to be z is equal to zero point 0.1 because they're saying 100 plot 100 by 1000 like 10%. So that the z will be 0.1. So can you calculate the first one? What is the value of that z? X minus mu by sigma x we have a 700 minus 662 upon we have the 32. Is it? So 10 to 8 963 by 32. It came 1 point how much? 187. So now we have to calculate the P of x greater 700. It means P of z greater than 1.187. So we can do 1 minus P of z less than of 1.187. Can you tell the value how much it will come? This is the table that you will get it. It's a point. I think that it's a point eight is there. So it will come 0.12. It means 12%. So expected plot will be 0.12 into 1000. It will become 120 plot. Is it? Can you do the similar way for the second case? I'll just wait for 2 minutes. Can you try? Or shall I? Okay, so I'll try.
You try, sir.
Okay, okay. Just try.
Sir, I am getting answer as 0.3557.
Yeah, some like it's close only. Point 0.3. Oh, it says 650. It says 650 minus 662. 12 by 32 minus 0.375. So that Z will become less than. Okay, so it will become 0.353. So expected plot will be multiply by 1000. So 353 plot. So what will the last? What is the third question we have? Third question, what is the lowest yield of the best 100 plot? It means they have given the Z value how much? Zero point 0.1. Is it? So we know the formula Z is equal to x minus mu upon sigma. So x will become mu upon sigma Z. So mu, how much is there? We have mu, we have 662. Z is equal to zero point 0.1 into sigma, we have 32. How much the value will come? Answer. I think somewhere I'm wrong, huh? I think correct only. Tell me the answer. 650 side, no? Something? 665. Okay, so now we have seen, I think till now, is it clear now? Like that the probability distribution we have seen. We have seen the discrete and that is the distributions. That was the binomial that distributions. Then we have seen the Poisson distribution. In the continuous distribution, we have seen the uniform distributions. Then finally we have seen the normal distributions. Then the special case of the normal distribution is the standard normal distribution we have seen. So now we are going to see the sampling distributions. Let's say now the earlier cases were that whatever the things we were having, that was the population we were seeing, and we were seeing the probability for the whole populations and all. Now we'll see the sampling constructions and all. Let's say for a finite, like the distribution of all possible values that can assumed by some sort of a statistic, and sample of same size randomly drawn from the same population is called sampling distributions. Anyone can tell like what do you understand from this? Let's say we have the some population is there. Okay, we have some population of size n is there. So we are going to draw all possible sample. Okay, so that the sample we are going to take, like we'll take the sample. So what will be the distributions? That we don't know. That we have to calculate and all. Once we'll go into the picture, let's say we are going to administer some drugs and all. Let's say for the case of, I'll tell one example. When we are going to see the waiting time in a hospital for to get the appointment of the doctor or maybe to see the doctors and all. So that we know that that will be the positive distribution is there already. And if we check about it at a traffic, if that much number is going to that much car is going to pass from that time, so that also we don't know that's going to follow the positive distributions and all. But once we come into that, like real time examples and all, so we have the very huge populations are all there. We're going to take some sort of samples and all. So that we don't know. So that sampling we can do in a like again before the sampling also we have the different types of samplings are there. We have that random sampling. We have that variable sampling. We have the stratified sampling and all are there. So what is the distributions? Okay, for the statistic, for the inferential statistic, that we have to assume or we have to make sure it is the, and that should be the normal distributions. But in the starting, when we're going to take the draw any sample, that we don't know whether it's a normal, whether it's another or either anyway. So to make all these things, so we have to, we should know the what are the that like sampling distributions and all. So after that, we are going to compute the static of interest for each sample. Okay. Then after we are going to observe. Then we are going to plot all the histograms. Let's say we have 1,000. That is the population. Now we're going to all possible sample of size n. We'll take 10 sample of all of size 100. Okay, of size will take 100, and we are going to draw a uh, uh, histogram. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If we draw what is the for a first sample of this size, what was the mean value? Let's say this one. Let's say this one. Second one, third one like this. Fourth one like this. Similar way. So it should going to follow some sort of distributions. Let's say some it will like this, it will like this, it will come similar way. So they're going to follow some sort of distribution. That will not going to always the normal distribution. It's going to follow some distribution. So to know this that distributions, we have some other theorems and all are there. So that we will discuss. So we are going to find out the sampling distributions instead of going to find out this the population distributions and all, because that we have discussed in a broad. Now we'll come to the concise or at the that point of interest we have, because in a statistic always we are not going to take a full population, because in the biomedical engineering, let's say for the COVID vaccine and all, they didn't take the testing of the whole population, because that is the whole population of two Arab and all is there. So that we can't do. So they have taken samples. In that sample also, whatever the distributions, if that distribution does not follow the normal distribution, so that we have to increase the number of sample size, or maybe we have to increase the testing, like change the testing and all. That we have to see out. So that is the purpose of sampling, and that is sampling distribution. So and once we do the sampling distributions, so then we have to calculate the what is sample number also. Okay. So based upon that also we have to like for a proportion when we have the two that group to compare, or maybe like in the different case we will see, because now we are going to jump into the statistic. Like till now we have discussed the probability. Now we'll going to jump into the statistic and all. Okay. So, in the case of sample mean, we are going to assure of at least one approximately normal distribution under the three conditions. Like when we are going to do any of the sample mean like we have taken a sample, if they are mean, so it should be like approximately it is going to normally that going to distributed. Okay. Sample distribution under the three conditions when sampling is from a normally distributed population. What is the mean of this? When we're going to say like a sample we have taken, their mean is going to normally that distribution if when a sample is taken from the already it was the normally distributed people. That let's say it was 1,000 of sample was there, and from their sample we already know that like it's going to be normal distribution. So if you're going to take or draw the sample from that normally distribution, it means it's going to be like that sample mean is going to follow the normal distribution. So that is the first condition. What is the second condition? When sampling is that from a non-normally distributed that the population and our sample is going to be large. So first case is that when when the sample is that drawn from a normally distributed sample, that their size is whatever the large or small and all it is whatever it is there. So their mean is going to be also a normally distributed. Second case, when a sample is going to non-normally distributed, like when the like that let's say we have taken the 1,000 or 10,000 sample we have taken, but the thing is that that was not the normal distribution. So means if we take the whatever sample we take, if the sample is large, it's going to follow the normal distribution. So again the question will come. So what will be the sample of large? What will that will be low? So in the statistic we have the n is equal to 30. If any sample is going to be below 30, we'll say that small sample. If any of the sample is going to increase the or maybe the more than of 30, we'll say that's a large sample. Okay, that we will see in the t test and all that we'll see. So if we're going to increase the number of size, that the sample large, it's going to be automatically it's going to fall under the category of normal distributions. So that is the second case. But the third case is that when a sampling is from a population whose functional form is unknown to us, as long as our sample is large. Whatever, it's the second and third case is it's a similar or they're going to complement each other. When we know the any population that we have the if the sample is as much as large, it's going to be always going to be a fall under the category of normally distributed and all. Okay, so means we're going to take that sampling distribution is a probability distribution for all possible value of the statistic computed from the sample of size n that we have discussed. Second one is that sampling distribution of a sample mean x is the probability distribution of a random that variable x bar computed from a sample of size n from a population with a mean of mu and standard deviation of that is sigma. It's a similar way that what we have seen. So now we'll come to the what will be the value or sampling distribution of the mean? What will be there? The mean of sampling distribution is equal to the mean of the parent population and standard deviation of a sampling distribution if sample mean it's going to be that is the sigma by root under n that is going to regardless of sample size n. Can anyone explain what do you mean by this? Mean of sampling distribution is equal to the mean of parent population and standard division or sampling distribution of a sample mean is sigma by n regardless of sample population. Any idea? Like it's actually a central limit theorem actually. Means they are saying like that mean of sampling distribution will become going to mean of the parent population when the sample will be the large. Second one, according to the central limit theorem, that going to tell the shape of the distribution of a sample mean become approximately normal as the sample size is going to increase regardless of the shape of the population. So that is the central limit theorem. They will tell. It's going to tell like okay, when the shape of the distribution is going to tend or it's going to skewed like it's going to be like toward the normal distribution when the sample is going to increasing like continuously. When the sample size will be the n is equal to 3, so that there is no chance that you will sometime will not get like that is the normal distributions and all that will not see if n is equal to 10 there might be they're going to tend toward the normal the distribution when it's going to beyond of 30 or 40 50 and all so it's going to toward the approximately normal as the sample size is going to increase so that is the one two properties will say that will the mean of the sample distribution is going to be like mean of the parent population and second one it's going to be like central limit theorem. So if you're going to sample means of that we are going to standard error will be counted as like sigma by root under n. Okay. So now we will see like one example based upon that. Suppose that it is known in a certain large human population that the cranial length approximately normally distributed with a mean of 185.6 mm and a standard deviation of 12.7 mm. What is the probability that a random sample of size 10 from this population will have a mean greater than 190? Can anyone just try to solve? Mu they have given 185.6 and sample size they have given 10 and standard deviation they have given 12.7 like it's sigma and they have given the x bar also 190. Just tell me what is the value. So we know the value of the z is equal to x minus mu upon sigma, is it? But if for sample mean that sigma it's going to x like it's going to be sigma upon root under n. So effectively this formula will become sigma upon mu upon sigma upon root under n. What is the x value? 190 minus 185.6 upon sigma. How much is the sigma? 12.7 upon root under 10. Can anyone tell the what is the value of z? I have to see the calculator actually. I think z value came 3.3, 1.3, and then 190 minus 8.5. How much it came? Can you please tell? I don't have the calculator here. Oh, it is 190 minus 185.6, 4.4, and root under 10. Root under 10, 3.162. It will come 1.10. Is it? 1.10. So now we have to calculate that they are getting mean greater than 1.10. What is the value? 1 minus P of Z of less than 1.1. So 1 minus 0.87 something will come. It's going to be 0.13. Is it? I think this will be clear. See, that we were seeing the earlier, it's a full of population, like it's in the poverty. Now they are saying sample size. When the sample will come into the picture, so that standard error will become sigma by root under n. So now that we have the second question we have. Second question, can anyone tell what is the second question? That question we have mean and standard deviation of a serum iron value for healthy men are 120 and 15 microgram per 100 ml. So this is the it's going to be redundant. What is the probability that a random sample of 15 normal men will yield a mean of 115 and 125? So Miss n is equal to 50, and we have the mu is equal to 120. Standard deviation we have 15. So how come it will come? Z is equal to x minus mu upon sigma upon root under n. Okay. So means so first one we have the 115, then second one we have 125. So first we'll go with the first one. So 115 minus 120 sigma, how much we have? Sigma we have a 15 root under 50. That one value will get. Second will get 125 minus 120 upon 15 by root under 50. We'll get one value. Can anyone tell what is the value actually? It's going to be more or less 5. It's a 7.15, 2.25, 2.2. It's somewhere 2 point something will come into the picture because it's a 7 point something will come. 15. So 7 is to 14. So 2 point something will come. And 125 minus 120, it's a 5. So 2 point something will be by 5, like 5 by 2 point something, it will come 2 point something. So I think it will come 2.36. Okay, I have the value. So just to 1 minute. Can you tell the value actually? I think it's a point 2.36 minus. It's going to 2.36. And now we have to calculate the probability. Probability of between minus 2.36 into Z 2.36. Just tell the value how much it will come. We can do in a two part. Minus 2.36 202, probability of minus 2.36 0 plus of, can we do like this? How much it will come? Can you please tell? Hopefully, you know that how to see the table and all. Can anyone tell, like anyone is there that who doesn't know the how to see the table? Shall I go ahead or I just shall I explain?
Yes, yes.
Okay, I'll go ahead with that. So I think some value will come. So you can just check with the. So I think this part is also clear. So now we are going to check like what is the point estimate of a population proportion. Okay. So suppose that a random sample of size n is obtained from a population in which in each individual does either they have some characteristic or not. So sample proportion is going to be like it's a x by n. How come? Let's say I was having some 100 population was there. I have taken some proportion. How much proportion we have taken? Let's say some 20 people we have taken by 100. So how much? 0.2. It means 20% we have taken. Means 20 that is the proportion of 20% we have taken out. So it's going to be point estimation of a population. That is a proportion. It's a one sample size we have or a one population we have. So this concept is actually a how much proportion we have taken from a sample like a population. So in the similar way, if we have the two population, so we'll get a two proportion, P1 and P2. That we will see like sample size, that sample, that number we're going to estimate. I will tell you the brief summary also will going to explain. Okay. So proportion itself is like I have taken some sort of some proportion. Let's say it was the full one was there, but now you have to divide into two parts. So 50%, that is the half proportion to the one, and then another half to the another one. Okay. So when we are going to calculate the any proportion, so it's going to be x by n. X is the sample number, sample size, not sample number. Sample number is going to be like some number of sample of size n. So that is going to be like x. So it's a sample size, and this one will be going to become population. So I think this is the all about the population proportion actually. So by the name itself, we can know that how it's going to vary and all. Then after we have the like how that what are the target parameter in the any cases. When we are going to have the mean and average, it's going to be always the mu. It's going to be quantitative. And if you're going to P, it's a proportion. It's like that is a proportion, percentage, or fraction, or the rate. It's going to be qualitative. Will not tell the number. It's going to proportion of how much percentage we have, how much proportion we have. It's a more or less it's a qualitative. Like it's going to more of qualitative, not the quantitative. But if you're going to say like mean and why I'm saying that it's a qualitative in the general we can term as this as a quantitative, but in the statistic we have to know the exact number. Even though we know the proportion, we know the just see we'll say the proportion it's a 20%, 30%, 50%, or maybe the half or one fourth. We don't know the exact number. It's giving the idea of the qualitatively, not the quantitatively. So don't get confused like no, I know the percentage, so I know the percentage, so that should be the quantitative. No, in the statistic, it will be the always the qualitative. Why I explained? It's because that is not going to give the exact picture or exact number of the data or the sample. But if we have the mu, mu means they will going to give the mean on average. That mean we are going to know that because from a sample or from a population we will take, they're going to calculate the mean. So we'll know the exact number. So it's going to be quantitative. Okay. So then we have the shape. Shape I already told like it's going to be like how it's going to be a behave. Maybe it's going to normally or it's skewed somewhere or maybe that like flat and all it's going to be. So shape. Then the center. Mean of the sample the distribution of a sample proportion equal to the population proportion also. It's another property we have for the sampling distribution. Then spread. That standard deviation of the sampling distribution of a sample will decrease when the sample size is going to increase. Why? It's going to give the confidence. Let's say I have very like that narrow or maybe the strict region. I have the only 10 population, like a 10 sample size is there. I have to calculate and all. So in that case, what will happen? The chances of the error will be high. That might be the type 1 error or maybe the type 2 error. Why? We don't have the freedom to to quantify. When the sample size is going to increase, we'll be having the confidence interval is like that narrow, like it's going to be like wider that the confidence interval that we will also discuss. So some question will come like this also. What will happen when the sample size is going to increase? What will happen in that case? That standard error is going to decrease, or when the sample size is going to increase, that is going to follow toward the normal distributions. Okay, so I think hopefully this is the clear actually. Is it?
Yes, sir.
Yeah. Uh, I'm going bit slow because I have to cover bit of more topic today. So now we'll come to the distribution of the difference between the two sample mean. Now we were seeing the only one. We were having what you can say, like it was the value of a standard error was there. What was the formula was there? X minus mu sigma upon n. So now we have the x1, x2 will be there, mu1, that is the mu2 will be there. Okay. So that for that case, what will be the like how we are going to calculate? So it's going to be a whenever we are going to solve a problem or we are going to investigate, so we'll take two group. In a biomedical, as far as I know, like when you're going to like we have the compare whenever we don't have the two population, what will take one population will take as a placebo group. Placebo group, it means they're not going to take part in the study, but the second group is going to take part in the study. Let's say I have to administer the drug for some population. Maybe it's a common for the all populations and all. Maybe it's for the child, or it's for the it's going to young also, and it's going to be the old people also. In that case, that population is a single population. So if we're going to compare or effectiveness of the drug or anything, we have to take a one that's going to dummy that the sample. So that sample will say placebo group. Placebo group means it's going to be like that group. They're not going to take part into the study and all. But we have kept as a baseline. So, so for that case, we have to like find out the things, and then based upon that, we are going to focus on the true population. Let's say now we have that some study will be there. Okay, now I have to administer the drug. What will the efficacy of the drug on the young population? What will be the efficacy on the like it's going to be old people and all. So in that we have the two groups. So we sometimes that we don't might need the placebo group and all. Sometimes. If we can take, so it's going to boost our study or robust the method of the study. So in that case, in an investigator may wish to know something about the difference between the two population mean. Okay. Then after in one estimate, that is a investigation, a research may wish to know if it is reasonable conclude that two populations are different or not. It's something. It's some similar case and all. It's a biomedical case or maybe the statistic. So we have to create a scenario or we have to create a hypothesis whether that anything I'm going to conclude whether it's going to that their mean are different or not. Then then the second situation is that the researcher may desire knowledge about the magnitude of the difference between two population mean. Once we know that okay the differences is there, whenever we know that okay some differences are coming between the two population, so then we have to know the what is the magnitude, what is the quantified value. Let's say sometime in the starting the main purpose will be first we have to know whether any difference is there or not. Once we'll get to know that if there is any difference, we have to know what is the actual difference actually. Okay. Actually, so means we have to find out the value also. So it's statistic is nothing about the like we'll just say the claim. We have to tell the what is the exact number, how much percentage difference is coming between the two population, or what is the value and all. Then the one more example we have, like for example that someone may want to know the whether or not the mean serum cholesterol that level is going to higher in a population of a sedentary office worker than in the population of the labor. One population is just that is the sedentary office worker. Second population is the laborer. Then after we are going to calculate whether how much they are differ, whether any differences is there or not, then how much is the differ. So whenever we are going to make any claim, whether it's going to differ or not, if it is there, so then we'll tell how much. Means we have to quantify. So that is the purpose of that. So for that, what will be the sampling for the known, that is the known population? It's going to be like z is equal to x1 minus x2, then mu1 minus mu2 upon, it's something that we know that value now, x minus mu upon sigma upon root under n. Now it's become x1 minus x2, then mu minus mu2, then sigma by sigma 1 by sigma 1 square by n1 plus sigma 2 square by n2. So that will see the problems that in this will come when we're going to solve the t-test, like when the population will be having the two different mean and all. That we'll see. We'll going to systematically we'll see the t-test also, like f-test and then ANOVA test and all we are going to see f-test and chi-square test and all we'll see. And will in that conclude also when we have the single mean. So from a simple population, when we have the two different population, when we have the population not the single proportion, then two proportion, then after we'll see like some sort of that is the correlation also we'll see. Okay, so now for the proportion also we can see z is equal to p hat minus of p into 1 minus p by n. It's nothing, p into 1 minus p, it's nothing, is a p cube. It's a probability by n. So that we'll know it's going to be like this and then p hat and all. So that we can calculate and all. So that once we'll solve the problem, so that we can see. So that the sample distribution of a sample proportion would be a constructed that is experimentally in the exactly same manner that we have done for the mean and difference between the two means also. Then we have the this was the single proportion. Now, if we have the two sample proportion, what is the value that we're going to calculate? Z is equal to similar way p minus p2 minus that's a hat p1 minus p2 upon that the same thing will come that is the comes into the picture here. So I think this thing will come that will get to know that more when we'll solve the problems and all. So we'll solve on each cases. Like I'll solve problem on the single cases, then two proportion mean, a single proportion, double proportion also we'll see, and we'll try to solve like what will be the relevant to your the current week assignments and all. I'm not going to solve the same assignment, but we'll solve similar type of question. So that is going to help you for the for the particular week and all. See that the over the span of 12 week, we'll solve each and everything in a detail. So now we are going to that is the summarize. Let's say for a z transformation for a single mean that we know that z is equal to x minus mu upon sigma by n we have seen. If we have the two different mean is there, similarly we have done z transform for a sample that is a proportion for a single proportion. This one is for what you can say two mean proportion. Okay, so now this is the like how to calculate and all. So now we can calculate the what you can say sample number also. How come z is equal to we know x minus mu upon sigma by root under n. So we have to calculate the n is the sample number. We can calculate sigma by n that root under n into z into x minus mu. Okay. So similar way we can calculate. So it's actually x minus mu is nothing is a standard error. Okay. So now, like we can calculate like a, it can go sigma into z upon standard error root under sigma upon n. Okay. So similar way, we can calculate the n also here. So it's a like method to calculate the sample number or sample size. So can anyone explain what is the confidence interval? Confidence interval. Till now, we have to discuss how can we calculate the point estimate or maybe sample number and all. Now we have to jump into the confidence interval and we have to set the hypothesis and all. Can anyone tell what is the confidence interval?
Sir, it is a range, like in which we can have a prediction.
Yeah, confidence interval is something like we have something the power or maybe the something the area we are going to say something about that. Let's say I'm saying 95% is the my confidence interval. It means 95% of the time is going to be it's correct. Is it?
Yes.
It's a similar way. Let's say it's a something like we are going to say that much confidence we have, and that the remaining will be the 1 minute that going to be alpha. Alpha is like that is the level of confidence. Confidence interval level that is the level of significance. It means point that is going to 5% or 1% in all. It's going to tell about the rejection area. So means that much percentage of okay, there is that much chances is there, that much percentage of the chances is there that's going to be a like fail or it's not going to quantify and all. So we're going to see like well, one will take the example like since the administrator of a very going to large hospital is interested in the mean age of the patient admitted to the his hospital in a given year. So in that case, he may consider if we're going to take all if we're going to take the all record of the that the patient and all, it's going to be like very expensive and all. In that case, what they will do, they will take the sample and then they're going to estimate mean age of the patient that admit here. They will not go through the whole record of the admit patient and all. How will go? That will see like then based upon that they're going to my that I have the confidence of 95% that my data is correct. Whatever I claim, it's that much will come. Or a physician in a general practice may be interested to in know what proportion of a certain types of the indicated the drug it's going to that going to be treated and suffer undesirable that is side effect and all. So it's something like they will get to know that. Then based upon that, they're not going to do on the whole population. They will take some sample. Then based upon that, they're going to conclude. So our main aim for the statistic is to we'll take some sample size and then based upon the sample we are going to tell the estimate of the population. Okay, or we'll tell the inference for the population. Then, after we have a point estimate is a single that is going to numerical value used to estimate the corresponding population parameter. It can be of anything, maybe the mu and mu sigma and all. Interval estimate is going to they will going to give the two numerical value defining the range of the value with a specified degree of freedom, most likely include the parameter being estimated. Let's say I'm saying like any of the drug or maybe the BP and all, it's going to be that much range if it comes or not. Like for a single, okay, that HRV is there, that is that heart rate variability, maybe 1, 2, 3, 4, 5, 6% and all it is there. So that is going to single point or point estimate. For the interval estimate, like for the BP monitor, it's going to be like 120 to 80 is the normal. That is going to baseline. So if some population have 140 to 90 or 140 to 100, so something. So in that case, it's going to be like interval estimate. So for that, we have to. It's very important to know that like we have to appropriate estimator. We should know. Note that a single computed value has been referred to an estimate, and that will tell how to compute this value or estimate. It's going to be like estimator are going to. It's like a similar way. We have this all population number of population and corresponding the value of that xi. So this is going to be estimator for a mean. Similar way, it can go sample mean. Sample mean we can calculate like a sigma like it's going to be like x minus mu like sigma upon root number n like it's going to be z value. Okay. So similar way it can go. So it's a similar way. How can we do it? Like it's a estimator. So for a sample population, it's I already told like it's taken from the one actually draws from a sample. Target population is the population about which one wishes to make an inference. Sample population, like we have 1,000. We'll take five sample of size 200, 200, 200. Then after we are going to like target population is like it's going to be like based upon this. Either sample is going to make the target about this. Like we'll take how can we infer and all. For confidence interval to be valid, sample must be the random and sample size n must be the large. Okay, so it's very good to have the very good number of sample size and all, but we all know that we have the restrictions in the biomedical. Why? When I'm going to take any of the human data collection, so all before data collection, we have to take the permissions. You know, they so there is a board of institutional review board. We want to do the any testing. If we want to do some testing and all, on the human also, sometime on that animal also, we have to get the permission from that the board or committee when we have to start the experiment, and there is always high chances or there is a high uncertainty that people will not turn off, because it will take some 2 months, 3 months, 6 months to take the data collections. Okay, so if we have the number of data is more, it means we have the good thing, like we can make the conclusion or the claim it's going to more
വച്ചിട്ട്
going.
പറയും അത് അവ
Sorry.
അയ്യോ
Okay. So we can make the claim it will be the more. Any doubt is there, or either if the mic is turned on, so please switch off the mic on. Okay. So whenever the data will be having more and more data, so we can make the claim it will be the more going to reliable. And if we have the less number of data sets, so it's that my data and my results will be not that much reliable. People will not going to like trust the data and all. That's why in Springer Nature and paper and all, they will going to like they will be focus. We have the when the number of the data or number of the sample size is going to be like more and more. Okay, so this is the one case like when the sample must be random and sample size should be the must be the large, so that it's going to be like that the confidence interval is going to valid. With the similar case we have like standardized that normal distributions, we can go like this is for actually for a like that the sample size of the large of n, and that we know the value of sigma. So mu will be the x plus minus z of alpha by 2 sigma upon root under n. How can we calculate? Like, if this is going to be like z alpha by 2, it's like significance level and all, and t value. So t is going to be like that is the student t, that is the distribution. For a small sample, it's going to be n less than 30. And this is for valid for n greater than 30 and all. Okay, so this will see a small sample like t distribution. In that also we will be having some cases will be there, that also we will discuss in a detail. So how we can calculate the what we can say confidence interval? Confidence interval we can calculate through the x of plus minus z of alpha by 2 sigma upon root under a by n. Okay, so it's going to be confidence. It will give the value of minus of like x minus z alpha by 2 sigma upon root under by n to, let's say that the mu to x plus z of alpha by 2 sigma of root under n. That will give the value. So that is going to be a confidence interval. So we can see here like when the t distributions, it's actually valid for small population or small sample size. So it's going to be not going to follow the normal distribution. When the sample size is going to increase, so they're going to tend toward normal distributions and all. It's a similar formula. This is going to number size. This is going to t like we'll get the value from the table t value for a that confidence level, and that is the degree of freedom. Degree of freedom, how we'll calculate that also we'll see. Then we have the confidence interval that this part we all know that this is going to be confidence interval, like that the area under the region, and this will say rejection area. Okay. Then for a population, that is a proportion also we can see that was also we can calculate like here 0 to p of plus minus 3 p of 1. We all know that why we have taken from the that the 0 to 1, because when we'll say the proportion, we'll say the percentage, it can't go the minus, is it? Because when we talk about the proportion, it will not go to the either 0 either 1. That 1 will be the 100%. 0 means there is nothing was taken out. So in that case, sigma p, sorry, that is sigma p. So means it's going to be like from 0 to 1 itself, because it's a proportion. It's going to, we told like it's going to be some total 100 is there from, sorry. So there is like for the that cases we were having x of plus minus like z of alpha by 2 sigma upon root under n. But for this case, what we have 0 to p plus minus 3 sigma p of 1. It's going to be always 0 to 1 itself. Why we told? But because the proportion, it's going to be talk about the like how much percentage. So that can't go beyond of the 0. Maybe the negative one. Either it will be the 1, either it will be the 0. So now we'll talk about the sampling that we have to, what type of sampling we have seen that I think that is the purpose sampling, means sample unit is selected with the definite purpose of a view. Okay, but in the case of biomedical, whenever we are going to do the statistical analysis, we have to tell all like it should be the random sampling. Why? Why? Can anyone tell? Because when we're going to take in biomedical, we have to take by the definition itself, if you see one in which each unit of population has an equal chances of being included in it. It means we're going to cover the whole population. But if we talk about the purposes sampling, we'll take we have defined the purposes based upon that we'll take a targeted population, but we can't generalize for the whole population. When we have the stratified sampling, it's a entire heterogeneous population. It divided into the number of homogeneous group, usually terms as a strata. It's again we are going to divide into some groups, but we can't generalize for the all group and all. So that is a similar way is the systematic sampling also. Okay, so this is something we'll talk about. Then we have the now we'll come to the test of significance. That till now we have discussed what is the sampling distributions. We have seen how to find the confidence interval and the level of that is significance and all. Then what are the type of sampling? Now we'll see the test of significance. Now, if when we talk about the sampling theory, so we have to know that what is the test of that is significance. That will be able to decide on the basis of sample results. The division between the observed sample statistic and the hypothetical parameter value. What is that actually? Test of that is significance will say how much deviation is there from the sample statistic and the some parameter like it will tell like a statistic value we have that mean, that is the median and the mode is there. Okay, then the hypothetical parameter will be having like that will be going to level of confidence or the confidence interval and all. What is the null hypothesis? Null hypothesis is the hypothesis that is going to tested or possibly rejected under the assumption that is true. Is it? Will tell Whenever I have to test two data set, I'll keep the actually camera. Okay, so what we have a null hypothesis. Null hypothesis is something like, when hypothesis is going tested or possibility, we have to reject it under the assumption that is true. Whenever I'll say, we have to check it like there is a two difference, there is a two different population have the different meaning or not. Or maybe I'll say training and untrained participant have the different, there is a different muscle activations or no. So we have to check the null hypothesis. Okay, I'll tell there is no difference between them. First, we have to hypothesize. We'll tell. Okay, first we're going to assume it's going to null hypothesis. Null means it's going to
உங்க கொண்ட எவ்வளவு பெருசா இருக்கு பாருங்க. சாங்கே வருது அப்படியே அதுவாவே.
I think your that mic is on. Can you please switch off?
ஓகே ஓகே.
Yeah. So first we have to assume that there is no difference. Based upon the statistic, we'll tell, okay, if there is a difference came, so we are going to reject the null hypothesis. So it means null hypothesis is something that we are going to make the assumption that is true. But we are going to reject it. Then we have the alternative hypothesis. It's going to be complementary to the alternative hypothesis. Means when we are going to say there is no difference. So means that complementary it's going to be like there is a difference, so it's was there. Okay. So in that case, what we'll say, in that case also we'll be having the two tail, like either it's going to be alternative test. First is the known as two tail test. Either mu is equal to, so H0 will be mu1 is equal to mu2. It's going to be, we'll tell, null hypothesis. Then alternative will be three cases. First one will be that mu1 is not equal to 2. It will say two tail test. Then H1 is equal to mu1 greater than mu2 will tell that right tail test. H1 is equal to mu less than of mu2. It will tell left tail test. That will see the possibility of, where it will comes into the picture. How come? First with the we are going to define the null hypothesis. It means there is no like both are having same that mean. There is no difference. Second will be okay. There is a difference is there, but will not tell which one is more, which one is having less. Okay. Then the that will become two tail test. Then we'll say, no, I'll tell like mu1 is greater than mu2. It means it's going to skew toward the right side. It's going to right side. Then H2. No, H1 itself, mu1 is going to less than of mu2. It means something we are going to say left side. So that all we'll discuss in the current. Then after can anyone tell like what is the type 1 error, type 2 error? I think that we have discussed in the first lecture itself, first session itself.
So type 1 is
True.
the alpha.
Yeah. Tell me.
Alpha error and null hypothesis rejected. True null.
Yeah. And type 2 error something that we have accepted, but it was wrong. Is it? And type 1 is
It's
something, type is something is
true.
sorry. Tell me.
Type 1 is which is true that we reject.
Yeah.
Type 2 which is not true but we accept.
Yeah. So, which one is more actually critical actually? I think both are equally, but if we talk about the type 2 is the more like critical because it's going to influence too much as compared to the other things. If you go deep into the statistic and all, it's going to more critical. Not. Like one error, actually, we should not do the any type of the error. Let's see when we'll say the reject the that we are going to reject the null hypothesis, but it's actually it was true. What will happen? The both population was having a like when the both population was having what you can say like there's no difference, but we have told actually okay there's a difference is there. So sometime okay will possibly will say okay fine, but the thing is that when now we are saying accept the null hypothesis, but there's a differences was there, but it will create more consequences as compared to the like type 1 error. That will comes once we'll talk into the it's in the in terms of clinical trials and all that will go into more effective and all. But we should avoid the both error. We should not like allow to the any that error to be happen. So for that we have to properly design the experiment. We have to properly collect the data. So there might be a like the noise will be there, something so that we have to smoothly conduct and all, then do the testing and all. If it is not done, it means either we are going to commit any of the error and that is going to spoil all the results and sometimes so there's like consequences will be the very high. Okay, so now that is the critical region and the level of that is the significance. So that area we are going to say the confidence interval. This and this area will say critical region. If any data possibility and our percentage it comes under these things, we are going to say uh, like it's going to be a fail or maybe this is going to critical region, and this is the level of significance. Either it will go into 5% or 1% or 10%. 10% visual that the in the biomedical that we are not going to see anytime in maybe the quality control or maybe that administrative control that is quality control that sometimes will be having more of level of significance, but in the biomedical we will only going to see 5% or the 1%, and this 1% it will come when we have the very critical that area we have to discuss, and sometimes like that any of the precision industry they're going to that make the biomedical instrument. So for their manufacturing, that error will be that 1% itself. Like we're not going to, but sometimes we'll not allow that much also. So it means something like it's we're going to be very critical. And if we talk about the like critical drug delivery or drug efficacy and all that, usually the people will keep in that the whole of the research paper will see that will going to say they will talk about the 5% of the level of significance itself. So I have seen that if we're going to take this region, that the one side means this side is going to multiply, so it will say one. So it's going to be one tail test. One tail test, it can be the right side or maybe that that's going to left side tail. And either if we say if I'm not going to say like which side having more effectiveness or which having more effectiveness, that will say two tail test and all. Okay. So I think we have discussed the right tailed and then left tailed also. If you're going to tell this is going to be a null hypothesis, and so that the same thing we have discussed also. Then after that, so now we can see here. This is going to be a critical region. This is going to be a rejection region, and this is going to be upper critical value. This is going to be a lower critical value. Okay. So I think till here it is clear, na? Can you tell? Or any doubt
Yes,
is there?
sir.
Yes, sir. Yes, sir.
Okay. So for the two tail test, when the level of significance will be the 1%. So Z alpha will become 0.005%, so 2.58. If the 5%, Z alpha by 2 become 1.96. So this value sometimes we have to remember also sometime. But the thing is that sometimes they'll give the value because they'll give the table also. So now, till now we have discussed all the things and we have introduced the hypothesis testing also. And we'll see the t-test. Can anyone tell the what is the t-test? What is the assumption of t-test?
T-test is for small sample size.
Yeah, that first assumption is should be the small sample. Any other? Second should be population should be the finite and normal distributed. These two should be followed. If not, then we can't apply the t-test. So t-test actually will say that equivalent t distributions. Actually, in the name of what you can say, and the scientist, it was kept like this. And if we compare, so it's going to follow normal the distribution, but their intensity is going to be having some difference will be there. So the t statistic will be x minus mu by s upon sigma n. That's why we didn't keep that is sigma, because sometimes that will not know the all samples mean, so that we have to take the sample itself. So that the sample mean it's going to look no, that not the sample means that the sample is external deviations actually. So s by n. So this is for single mean. Okay, so t is equal to x minus my x minus mu into sigma of s upon n. And one more thing we have seen, whenever we are going to increase the number of sample, like some that a degree of freedom when the two was there, because the n minus one will come the degree of freedom. And like when we have that three sample, so we have this one. So but it's going to when the sample number is going to increase, it's going to tend toward it's going to coincide the normal distributions actually, so that the variable is going to range from the minus infinity to plus infinity. Everything will be the as it is. It's going to be a like normal distributions. It's going minus infinity to plus infinity. But the thing is that only thing we have the sample, that the number of sample will be. Okay, so that number sample should be the 30. So in that, when we're going to discuss about the t-test, so this is for actually for simple mean. Once will come to the like how we can calculate the confidence interval that I already told, x plus minus t of 1 minus alpha by 2, s of that is a root in 1 like n. When we have two sample mean, two population mean, in that case x minus 1 that minus that x1 minus x2 plus minus z alpha by 2 and the it's going to root in sigma 1 square by n by n1 plus sigma 2 square by n2. So this is how we can calculate the confidence interval. It means estimator means plus minus, then the reliability confidence like coefficient. This is going to be a standard error. So now we have discussed all these things, and before we'll start the t-test for the next session, like that we're going to next class or the next session, we'll discuss for the single mean. Then we'll see the two population mean. Then we'll see the proportion also. That's also single, and then that is the proportion. Then after we'll see with that coefficient also, like correlation coefficient. So I think that's all for today. But we'll solve some problems. Like we'll have based upon the central limit theorems and all. Now this is the first question. What does the central limit theorem state? Can anyone tell the answer?
Option B.
Option
B.
yeah. Means like whenever we are going to talk about the central limit theorem, they are going to sample mean which is going to approach a normal distribution as the sample size increases. That we have discussed, like when this is going to be normal distribution. So first, if the sample size is low, it's going low, then it's going to indicate like then when you're going to number of samples will increase, it's going to follow the normal distribution. Why can't we that the population mean is equal to sample mean? This is the answer. First one, because it's not going to be always. Why? That population mean can vary. When standard deviation will differ or error will change. Okay. So this is not always the case. If that standard deviation or standard error will change, so that population mean can be like can change. Then that the sample mean is always nowhere distribution. For the case of central limit theorem, it's not going to be always. Why? Because we that is not going to that not going to relevant because when the number of samples will increase, but this conditions will become relevant when t-test case. Is it? So this can't be the answer. This can't be the answer. The sample variance equal to the proportion variance. No, it will change. They do not always change because the population have more number of sample, like more number of data set is there as compared to sample variance. That they do not always change. Okay, so that's also not always. So I think this question is clear now. I'm just
Yes.
explaining like why can't be the other answer
Yes.
also. Okay, so now the second question we have a according to the central limit theorem, the mean of the sampling distribution of the sample mean is equal to again the last question and here bit of difference is there. Just try to think and then tell.
Sample means, sir.
Again, think little bit. Actually, this the sample mean is actually a you know like a particular sample, not average of all possible sample. Okay. So if you talk about the central limit theorem, so they will tell like they're going to be like shape will be the like follow whatever the regardless of size. You know, like there that will go shape say that the shape of size is going to follow whatever it is there, but it whatever numbers that when the sample size is going to increase, they're going to follow the normal distribution. Sample mean it's a one sample case. Population mean it's going to be like they will going to talk about the population itself. So that for the central limit theorem, the means of sampling distribution of sample mean is equal to the population mean, not the what you can say sample mean. Sample mean will tell only about that particular sample, not going to tell across all possible sample. But the population will tell for all simple actually, all sample. So that the variance can be because of that is going to irrelevant because so they're asking about the mean, not the variance. It's going to be totally irrelevant. I think hopefully it is clear. Now we have the third question. Which of the following is the true about the standard error of the mean in the context of central limit theorem? Standard error.
Sir, option A.
So we know the value of a standard error is actually sigma upon root under n. Standard error is inversely proportional to the n, maybe sigma n. So means when we're going to increase this one, it's going to decrease. So means this is going to be option A. It can't be sample size increase, so it should not going to increase. It is equal to the population standard. No, it is equal to the population standard deviations. No. Why? When it will be going to be like when? Tell me. It is equal to the population standard deviation. When it will become the n is equal to 1. Because the sample, when we talk central limit theorem, it's going to talk about the sample. It remains constant regardless of sample. No, when the number of sample will change, like a number of sample will change, this will change, na? So this also can't be the answer. I think this is this option is okay, na?
Ah, yes, sir.
Now we'll go to the fourth question. Which of the following are assumptions required for the central limit theorem? Just think about. There might be other multiple sample can be there.
Sir, A
So
and B both are frequencies.
yeah, whenever we'll say central limit theorem, so whenever we going to increase the number of sample size, we are going to decrease the standard error. Standard error is going to decrease. So means we'll be having more confidence. So that will be the correct answer. And second will be the sample must be different, independent. It should not going to influence one sample should not influence to the other sample. Okay, so that should be the like this is the one assumption that will comes into the picture. And the proportion must be the normally distributed. No, that is not at all. It's going to be a necessary. It is. It will be the necessary when when we talk about the statistic test like t test or ANOVA and all. So for the this one, that can't be the answer. That the sample standard deviation must be known. No, we can calculate it actually. But for the case of t test and all, that should be known. Like this is another case. So for the CLT, that should be another case. So first option and second option is the correct option actually. Now we have the when constructing a confidence interval, which of the following factor will lead to the narrower interval?
Sir, option A and C.
Option A and
C.
C. So as we all know that the width of the confidence actually interval it's going to depends upon on what sample size, and second one will be the confidence label or interval. When the sample size increases, so our it will become a smaller standard error and narrow confidence interval. Is it narrow or wider? means smaller standard error will become. So means it's going to be like it's going to be a normal and the narrow confidence interval. So first option will be the decrease the sample size. It's going to wider the confidence interval will become. No, that standard error will standard error will increase, not the like what we can say confidence interval. Then decreasing the confidence interval, confidence level. There is a difference between the confidence level and then confidence interval. When we are going to decrease the confidence level, what will happen? It will become the standard error will also decrease, and that it will become the narrow. Increase the population mean it's not going to affect much, because when we talk about the sample here, not the what you can say, but it due to the sample like due to the population mean it's not going to change the width of the interval. I think this is the clear na, because we know the formula here
Sir.
standard error. So now we have the one question we have. In a population with a mean of 50, deviation is 10. What is the probability that a sample of 36 observation will have the sample mean greater than 52? It's a simple question that you can solve it actually. Just tell me what was the answer. Mu is equal to 50. Standard deviation is equal to 10. Number of sample is equal to 36. And they are saying it should be greater than 52. First step is to calculate x minus mu upon sigma upon root under n. Just tell me the value of z. I'll wait for some 5 to 10 minutes, like 2 minutes.
Uh, 0.2, sir.
Uh, I think that you are saying the value probability of the what is the z value? Actually, it came 1.2, and probability of z of 1.2 will become 1 minus of probability of z less than 1.2. So it's a 0.8 something will come. So it's going to be first answer. Okay. I think
Okay, sir.
hopefully it is clear. It's a simple formula based question only. Is it?
Yes, yes.
Now we have the another question. For a 95% confidence interval, the margin of error is 3.2. If the sample size is quadruplet, what will be the new margin of error? Tell me what will be the answer.
Yes, sir. 1.6.
Yeah, because we know the formula sigma upon root under n. Is it? And if you get alpha by 2 also. So actually it's a, so this value we know the 3.2, and this is the 4, 3.2 by 2, so 1.6. Okay. Now we have the, we can see here, margin of error decreases with the large sample size. Formula we know that margin of error is inversely proportional to the that new ME will become 1.6. Now tell me in this question, which of the following factor would increase the power of a hypothesis test? Power of the hypothesis test.
Don't know, sir.
We all know that when we're going to increase the sample size,
Yes, sir.
it's going to decrease the
Error.
error.
Yes, sir.
Yeah. Then after it's going to sample distribution will become easier to detect. So we'll get uh, more power to detect. So power will increase. So first option, decreasing the significance level. No. How come? When we're going to decrease the smaller significance level, we have the stricter region H naught. We will be not having the more and more to that going to reject. What will happen in that? Reduce the rejection region. So power will decrease. Okay, increase the effect size. How come? Like if we're going to increase the effect size, what will happen? Bigger the effect size, bigger the size, it's going to easier to detect. And that eventually it's going to increase the effect size, increase the population external division. It's not going to affect anyone. Okay, because it's going to overlap the maybe the both that's going to be a null hypothesis and then alternate hypothesis. So actually for this we'll be having that increase. Just say don't confuse with that whether it's going to, but it's going to increase the power. Increase the power means either it's going to reject or either it's going to accept. It's going to be like give the broader sense of like freedom and all. So that will give by increase the sample size, increase the effect size, decrease the significance that label. We don't have the that much power to power means it's going to they're going to limit the of your power. I'm not saying whether to reject or whether to accept. It's going to later part, but we don't have the broader power. Broader power will comes into the picture when we're going to increase the sample size or effect size. This is not going to affect too much because it's not going to affect the sample. It's going to affect the standard deviation. Then it will come. Sample is not going to affect too much. So that A and C will be the appropriate answer. Is it clear?
Sir.
Yes, sir.
Okay. So power improve with the larger sample size. Power improve with the larger effect size. That going to lower alpha, decrease the power, and higher population that the variability. It's again going to decrease the power. Means we have the more variability. It means more noise. We can't able to tell anything about that. So now we have the another question we have. When determining the sample size needed for the confidence interval, which of the following statements are true? So we have the R. It can be the multiple sizes. Just tell me. Just think about that. A small desired margin of error requires sample size. So we know that margin of error inversely proportional to the total n. It means it's a correct. Is it?
Yes, sir.
Yes, sir.
Higher confidence level requires larger sample size. It's also true because
Yes,
Yes,
sir.
sir.
we know the formula also. How can we calculate that the sample size? We know the z is equal to x minus mu upon root sigma upon n. So confidence level, so it's going to be z of alpha by 2. So it's going to be that going to directly proportional actually. So it's going to increase. A larger population variation with the variance requires smaller sample. No, because the population we are not bothered about the population. If population variance is going to be more, it's going to be for a larger population variance sample size it's going to be affect too much, but it not our sample related. It's going to related to the population. So that can't be the answer. Sample size is independent of the population size. It means is it true? Is it? Sample size will be the independent of the population size. So I think this is
Yes.
the clear, no?
Yes, sir. Yes.
So now we have some example. Just please solve it. A researcher is testing a hypothesis that a new drug reduce the blood pressure more than the existing drug. So they have some drugs are there. So the null hypothesis is that there is no difference between the mean and reduction in the blood pressure of the two drugs. So it's a null hypothesis. A two sample T test is conducted and the following information is conducted. So we know that T is equal to x1 minus x2 minus mu1 minus mu2 upon root under sigma square by n1 sigma 2 square by n2. So this is a T value. So sample of 1, 2, sample mean, sample 2, pooled standard deviation. So sigma pool means it's the same. Sigma 1 is equal to sigma 2, sigma p is equal to 5 mm of Hg. So please just calculate how come it comes. We know the formula. This is the formula. And from the table, we can find out the value t of 0.05 by 2, like alpha by 2, and that n1 minus n1 plus n2 minus 2, we can calculate the value. Just tell me what will be the answer. Tell the value of the t value, how much it will become t statistic value. It's a t test of two population. Is it?
Yes, sir.
So just put the value in that t value, we'll get the value of t. It's going to, we'll tell the t calculated. After that, we'll calculate the t of, what you can say, t of tabulated. We'll take from the table 5% of significance level and of 50, 60, 90 minus 2. 50, 60, no, 50, 60, 110 minus 2, 108. We'll get us some value. So based upon that, we have to, whenever the value will be the t calculated is more than that of t tabulated, we'll tell we have to reject the hypothesis. Is it?
Sir, where to put pool standard deviation value?
Here. Sigma 1 is sigma 2 is same now.
Okay, for both five.
Yeah.
Okay.
Pool standard deviation means it's a both for both it is same.
Sir, and what to take as mu value?
Sorry.
Mu value, mu.
Mu value we have now 50, 60, x1 minus x2 and 12 minus 10. This one. Mu 1, mu 2. Mu 1 is the 12.
That is a sample size, no? 15, 60.
Okay. Sorry. X1 is This is the formula, na? I'll just what is the formula? Actually, tell me. There will no concept of mu, na?
Yes, sir. So, I mean, mu is not given.
Mu is not required actually, is it?
Okay.
So t will be x1 minus x2 upon sigma square by n1 plus sigma 2 square by n2, because when we're going to take a simple one, so t will be the x minus sigma upon n, na? There is no concept of x1 and x2 now. Like that the mu and all, na? So now you can get the value. So when we t calculated is greater than the t of tabulated, so we have to reject the null hypothesis. So we have to get the t tabulated as at this alpha by 2 level, like 0.05 by 2 of 108. How much it came? Can anyone tell?
1.659.
This value that tabulated.
Yes, critical value. Yes.
What about the calculated one? We have calculated here. How much?
That is around 2.09.
2.09. So we have to reject the null hypothesis. Is it? So this is the answer. Is it?
Yes, sir.
Okay. So now the next we have. A factory light bulb with a known population standard deviation we have. How much we have? 120 hours. The company want to estimate the average lifetime of its light bulb with the 20-hour using a. So how much is that mu? 20 hour. Is it? No. Like error. And confidence interval, how much they have? 99%. We know the formula of a standard error is z of alpha by 2 sigma upon root under n. Is it?
Yes, sir. Yes.
So can calculate the n. We know the value of standard error is 20. Sigma is 120. And z value we can calculate from the 99% percentage. How much it will come? That will be the two-sided. It's going to be a 2.58. Is it? What's the value of n?
Yes, 2.57. Yes.
We have three more questions only, not more than that.
2.576.
It will come to 14. No?
Yes, sir. Answer is 2.
Okay. So can we go to the next question? This
Yes.
is the next question. we have the how much. Consider a situation where researcher is testing a new fertilizer improve the crops or not. The null hypothesis is that the mean yield with the new fertilizer is equal to the mean yield without it. A significance level of 0.01 chosen following sample data collected. Mean of yield, like it's a x1, x2, n1, n2, sigma p. So now they're asking to calculate the p value. So last we have calculated t or the z value, na? So now we have to calculate the p of t. It's just an extension of the last question. Can you do it? Like t will be the x minus x2 sigma square by n1 sigma square by n2 sigma 1 sigma 2, like it's a sigma 1 is equal to sigma 2. So again you can calculate the t value. So that will be and now based upon this t value you have to find out the probability. So first we have to calculate the p of how much, uh, 40 35, it's a 75, because the degree of freedom will become n1 plus n2 minus 2, so it becomes 73. So 0.005 or 73, it will come some value. From t calculated, it will come some value. If it is t calculated is greater than the t table came, so we have to reject it. So we have the two options: reject it like this, like this. Then after that we have to calculate the p of t calculated. Then we'll get the p value. Just tell how much it will come. I think that steps are clear now.
Yes, sir.
So that answer will be how much? Can you tell? A or C?
Answer, sir, A.
Okay, answer will be A. Okay, shall I go ahead? Next question.
Yes, sir.
So now the next question we have a an engineer is designing a new component and want to estimate the mean time to failure. Based on the preliminary data, the engineer knows that the standard deviation of the time failure is how much? 15 hour. To estimate the mean time to the failure within 5 hours with 95% confidence, what is the minimum sample size? So error is given. How much? 5. With Z alpha 95%. We have to find out the form n. How can we calculate? Standard error, we know that Z of alpha upon sigma upon root n. Can we calculate the n? Is it?
Yes, sir.
What is the answer? Can you tell? Because for this, we'll get the Z alpha 1.96. So if we calculate Z into sigma upon E to the power whole square, Z 1.96 into sigma, how much we have? 15 upon 5 to the whole square. How much it will come?
Sir, 34.5.
34.5, so closer to 36. Is it correct?
Yes, sir.
So the last question we have. A survey is conducted to the estimate average height of the adult in a male city. Sample size is 100. Sample mean is 175. The population standard deviation is known to be the 10. Uh, this is okay. What is the 99 for conversation interval for the average height of the adult male in the city? Can I tell? n is equal to 100. Then we have the x is equal to 175. Sigma is equal to 10. So confidence interval, how can we calculate? X bar plus minus z of alpha sigma upon n. Can we do it like this? We have seen this formula, no? For the 99%, we know the value is 2.58. Is it? Is it correct? So what is the answer actually? Tell me. If you calculate x bar, how much? 175 plus minus 1.9. No, no, not 1. 2.58. Sigma, how much we have? 10 upon 10. Is it? It will go 175.2.58. 175 minus. So it will become, answer will become A. Is it? Is it clear, na? Or any doubt is there in this? Hello? Okay, so this is the last question actually. The researcher want to decrease the width of the confidence interval to the within 1.5 while maintaining 99, that the 99% what is the sample should be there. So that we all know that. How come? N is equal to, we know how much? Z of sigma upon E by whole square. Is it? Z we know 1.5 centimeter. 1.5. Sigma we know from here only. How much? 10. What is the error? Error, we know the only one. How much it will come? 15, 20, 2 to 5. We don't have the answer for this. So, shall we wind up?
Yes.